Hello everyone, you are welcome to our multivariate calculus lecture videos. I want to get a quick recap of what we've already learned in calculus 1. That has to do with single variables. In calculus 1, we went through what we call the total derivative with some notations expressed below. We had the f dx rewritten as f prime, the square f dx square as f prime prime. It means that if I have the total derivative cube respect to the independent variable cube, I have f prime 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 and so on and so forth. So through to the nth derivative, I have it as y f to the power n. Now note that if I have y squared, it's not the same as writing y to the power bracket 2. This is a power square and this is a derivative, the second derivative. So we take note of that. We already know this. Now what do we have for multivariate calculus or calculus 2 or 3? It depends on your curriculum, but multivariate calculus, this has to do with multiple variables, so multi-variables. It means that your function can depend on 2 independent variables or 3 independent variables or more. So in this case, if I want to differentiate my function with respect to any of the variables involved, can I write it as total derivative here? And the answer is big no. This is wrong. Because it has more than 2 independent variables, I need to have a partial derivative of it. And this is correct. The independent variable x. Partial derivative respect to y. Partial respect to u. If I write it this way, everybody knows that it is having more than 1 independent variable. That is the message it carries instead of the total. Now you can also rewrite this as I not have this as z prime, but I can write this once as z prime. It's either zx, z subscript y, or z subscript u, to show that it is a partial notation. So we take note of that as well. Partial does not go with the primes, but they go with the subscripts. Having said that, we have various forms of partial derivative. Just as in the single calculus, you can differentiate once, you can differentiate twice, you can differentiate 3 times. We can do the same thing for partial derivative. If we differentiate once, I've already shown you, it's just the partial derivative with respect to 1 variable. This is equivalent to that, and this is equivalent to this subscript. I can also differentiate the terms twice. How do I write that? So look at this. Assuming I maintain my functions here, I maintain these functions here, I can differentiate this function twice with respect to certain independent variable in the function. I can differentiate the same thing with respect to x and then y, x and then y, partial. It means that you realize if I can rewrite or simplify, this becomes square of f and this becomes partial x square, as you see here. If I move to second stage, I have square here, del square, but look at this, it becomes partial y partial x. The next thing becomes del square, partial x partial y. The last thing, del square, so there's a square here, partial y partial becomes partial y square, and that is it. Or I can rewrite this as the subscript notation. If I don't use the partial derivatives, I can use the subscripts. So this means fxx. Differentiate f with respect to x twice. Now look at this one here. It's not going to be fyxy. These are not the same y. It's as if I already have my function in terms of x, which is this one, and I have to now differentiate it with respect to y. That is what I'm doing. So over here too, I already had the f with respect to y, which is from here to here, and I add respect to x. Alright, so here becomes just y as we would expect. So I have a term here called the mixed function or mixed derivatives. I have fy equal to fxy. Are they the same? That's a question for the course. do you think they are the same? We'll go through examples and then we'll get to appreciate what we have here. So that's the second partial derivative. Now there's a higher derivatives. It means I can move on to look at in three forms like this ones. This are higher, this higher, this higher. I can even move to the fourth higher derivative, the fifth higher derivative, so on and so forth. Example is I can look at fxx. There's a third order derivative. It means differentiate x 3 times. fxyz, z. First differentiate with respect to x. When you're done, differentiate with respect to y. When you're done, respect to z, and then the last respect to z. These are higher derivatives. Not to bore you with this notations, let me take you through examples quickly. And let me say this: all the rules you establish in the single calculus, product rule, power rule, quotient rule, and all those things, they still come into play here. So please don't forget about your rules. You still apply them in the partial derivatives. Let me quickly take you through example 1, where we are applying the power rule. Because it's a multivariate, what you do is that you always, if you're differentiating respect to, let's say, x, you hold y constant. If I'm differentiating respect to y, it means that you have to hold x constant as constant variable, and then you can do your differentiation. Don't forget this rule. No matter the expression, if you are taking one, it's assuming you are holding the others constant. Okay, so let's take this polynomial function. I'm differentiating respect to x here. If I take the first term, there's x there, there's no y, so I have the simple calculus. I'll have 6x. If I'm differentiating respect to y here, there's no y term here, so that part go to 0, plus, if I differentiate respect to y, I'll have 6y squared. I'm right there. Okay, so I don't have 6s plus 0, but the next term does not have any s part, so I can do away with the zeros. This is the first partial derivative. Let's move to the second partial derivative. I can still branch from here and then find xx. What do you think xx would be? It means go back to the zx and differentiate with respect to x again. I'll simply get 6. Okay, the same thing says go back to the zx and differentiate with respect to y. Because there's no y component here, no y term here, it means I'm going to get 0. Okay, the same thing, it says go back to zy and now differentiate with respect to x. Because there's no x term in the answer I had, I'll get 0. This one says go back to zy, this zy, now differentiate with respect to the last term y. And what do you think is going to happen? I'm going to get 12y. Okay, that is simple as that. If I want to move to higher terms here, or higher derivative, it says that you've already done this to xx. Now differentiate with respect to x. Because there's no x term, I simply get 0. It's just obvious. Now realize everything I'll do here will also be 0 because there are no even x or y terms here. Now if I move here too, it says your zyx. Now differentiate with respect to y, I'll still get 0 because there are no variables even involved. And the same way, if I move here, it says zyy. Now differentiate with respect to x, and that will give me 0. Assuming I had zyy, it means I'll go back to zyy and differentiate with respect to y. I would have gotten 12 as the answer. So you take note of how to differentiate this. Now back to the question. It says, are these two guys the same? Are they equal? Did we get the same answer to that to verify what we had here? Okay, so that's the first example on how to do a partial derivative. Let's see the second example. Now look at it. It is the same function, by just now multiply the last term by some x. Let me use a blue. I think the red is so not cool to the eye. Okay, so we are differentiating respect to x. I take the first term, I'll get 3 plus the second term, because there's x term there, I can differentiate it, and that give me 2y cubed. If I'm holding y constant and I differentiate x, I'll get 1. So that is what I have. Now zy, the first term, there's no y term, so that place is 0 plus the second term respect to y. If I keep x constant, I'm going to get 236y squared. So I can do away with the 0 here, it is not needed, and that is what I have. I can now move to a second derivative. If I differentiate respect to xx, it means that go back to x and now differentiate with extra x. You realize the first term will be 0 plus 0, but there's no x term there. Okay, so simply 0. So it's simply 0. Now it says that go back to the same xy and now differentiate respect to y. The first term was 0, the 3 goes to 0 because it's a constant, plus, can I differentiate respect to y? Yes, I get 6y squared. We are applying the power rule here. Okay, now zy respect to x. Please take no, you don't go back to the function. This doesn't go back to the function. No, it goes back to the zy and differentiate respect to x. I'm simply going to get 0 there because there's no x term. But zy gives me 12 y. Is this something I'm doing wrong? Yes. My zy, if I'm differentiating respect to y, I'm going to hold the x constant, so it means my x should still be here, and hence this is no more 0, but rather it's going to be 6y squared because I'm differentiating respect to the x. Let me take that again. Look at this term here, it is multiplying. So if I'm taking respect to x, as if I'll close my eye to this guy and differentiate the x prime. In the same way, if I'm differentiating respect to y, it's as if I keep this x and now differentiate this guy respect to the y. So that is what we have there. Okay. Again, are they the same? Is your mixed partial derivative the same? Alright. To an example where I would employ the product rule. I'm still looking at two variable system here. We already know from single calculus that if I have EAX and I differentiate this, it is AEAX. We know this. But now we have the A is now Y. Is now XY. How do I differentiate respect to X? It's as if I differentiate this exponent with respect to X, and what do I get? I get Y. Instead of A becomes Y. So I multiply Y here, EXY. Simply, if I want to differentiate respect to Y, if I differentiate the exponent, I'll get X. Then whatever I have is remain. Okay. Let me branch to a second partial derivative. It says XX. Now move back to ZX, differentiate respect to X. I'll still have my Y as constant. If I differentiate EXY prime, I get Y times Y. So Y squared EXY. That's what I'm going to get. Here I'm sure ZXY. ZXY means that this is where the product rule comes in, because I have two forms of two terms all with Y. So I maintain the first Y, I differentiate this guy, plus I maintain XY and I differentiate Y. Now they are primes. Okay, so simply this is going to give me if I differentiate respect to Y, I'm going to get YX EXY plus, if I differentiate Y, I get 1 times EXY. This is what I'll get. If I want to quickly do the ZY yx. Whatever I had from the z, I'm differentiating respect to x. Again, the product rule happens. I maintain x and differentiate the second term here. That will give me yexy plus I maintain exy and differentiate respect to x. I get 1. So this is the same as yxexy plus exy. Are they the same? You check that. Now zyy, I don't need any product rule because the y term is just on the exponent. I'm going to simply get x squared exy. Please verify these answers. Verify these answers, especially with the product rule. Okay. I think I have one more example. Let me move to sheet 5, where I had 3 variables. My function depends on more than 2 variables, so it's still multivariate calculus. I can't go through all the 3 branches, so I'll take the first part of the tree. I'll start from here. F of x, I'm going to get 3x cubed minus respect to x. I means I'm going to hold all the other constants. I get yz. If I differentiate x here, I'll get 1. Okay. Oh, sorry. Alright, so that's it. Let me move down from the same f of x. If I go to a second partial derivative respect to x, I'm going to get 9 that'll give me 9x my pen. Okay. Oh, sorry. Oh, 252. Sorry for that. Let me quickly go. All right, so this is where we are. What just happened? I'm on sheet 5. Okay. Everything is gone. Okay, so the first derivative, no, I'm through with this power rule. I was on sheet 5, so for 5. Okay, sheet 5. Oh, everything just went off. So I have 3x to the power cube minus 3yz. I want to move through the same tree, so I have x gives me 9x squared. I'm differentiating again respect to x. Now I realize that the second term here, there is no x term, so that place goes to 0. So minus 0. I don't have to write minus 0. You know that. Now if I want this fxy, it says that go back to this guy and differentiate respect to y. The first term gives me 0 because there's no y term there. Minus the second term gives me 3z. I don't need to write the 0, so it is simply negative 3z. Now this term here, go back to f of x and now differentiate respect to the z. The first term goes to 0, then the second term gives negative 3y. Okay, we can look at the higher partial derivatives. X simply is going to give me 9 to 18x. Xy, I'm still moving from here. Xy gives me 0 because there's no y component. The same way fxx will also give you 0. So this is how the higher partial derivatives work. If I want to move here, I'll have to find f of z first, and then let me see if I can help you out. That f of z gives me negative 3 xy. Zz will give me 0 because there's no z term again. Zy gives me negative 3x, and then zx differentiate respect to x gives me negative 3y. I can move down the train and so what is f of z? It will still be 0. What is f of zx? That will still be 0 because it's a constant term 0, so you can't do anything about that. If I want to move here, I can look for f of z, y, x, and that should give me -3. Any other term I add will be 0. You should see that. And here too, I can move to f of z, x, y, so I can get -3. Any other variable will give me 0. This is how the partial derivatives work. So I hope you take your time and go through the videos on partial derivatives and then take more examples on that. Thank you.